Dear friends, I am going to your third lecture regarding the digital logic families. Texas Instrument in 1964 introduced this TTL logic family, and in that TTL logic family, that is called a transistor logic family, they replace diode and transistor. Diode was replaced by the transistor. That's why the DTL family is replaced by a TTL family. And this is the great invention, you can understand like that way. Because when you are utilizing a transistor only, the speed of operation has increased. The calculations become faster. The computations become faster. And it is required for our day-to-day life nowadays. You know that we are going to next and next generation, third generation, fourth generation, maybe the fifth generation, etc. So where the speed is important, where the transistor logic is more important. So all combinational logic circuits, that is nothing but all digital gates, basic logic gates plus universal logic gates. They are going to be converted with transistor logic family and inside the IC forms. So that's which we are going to study, and the first gate which was invented was two input NAND gate, which was a backbone of TTL series, and using this one all other gates are going to be invented, or it is going to be modified, and all other gates are going to be prepared from two input NAND gate. So we will be studying the first two input NAND gate. What is the NAND gate? AND gate followed by NOT gate is known as a NAND gate. All input is going to be high, then and then only output is going to be high, that is AND gate. So the NAND gate is nothing but if all input is going to be high, then and then only the output is going to be low, that is NAND gate. Okay, so we'll study now the NAND gate. So 7400 TTL standard NAND gate, and the gate which is invented is called a standard TTL. Figure 14.10 shows a TTL NAND gate. The multiple emitter input transistor is typical of the gates and other devices in the 7400 series. Each emitter acts like a diode, and therefore Q1 and 4K resistance act like two input AND gate. The rest of the circuit inverts the signal to produce the inversions. So here we are going to study this NAND gate. Next slide. This is the circuit diagram of two input TTL NAND gate. Now you can see that input side, this transistor Q1 and 4K resistance. This transistor is having more than one emitter. Normally this is a base, there is a collector and there is an emitter. But here there are two emitters is shown. So this is two input NAND gate is there. And if the emitter is going to be increased, the number of input can be increased. So this is the typical characteristic of TTL circuits. Second important things, this one, totem pole arrangement, that is Q3 and Q4. Both are NPN transistor, they are connected in series. One sits upon other one. Either of the transistor is going to be on, and that way it provides the output. If Q3 is on, that means the Q3 is closed switch, the output is going to be high. If Q4 is going to be closed switch, at that time Q3 will be disconnected and output will be grounded, or that is going to be low. So this way, this is the total pole arrangement and multi-emitter transistor, that is the typical characteristic of all type of the TTL circuits. Remember, some of the TTLs may be open collector and tri-state devices. This will be slightly changed. Otherwise, this is the normal characteristic of all type of TTLs. Here, this is NPN transistor Q1 and hence the collector is N-type material, the base is P-type material, emitter is also N-type material. So, between base and emitter there is a PN junction diode is there. So, if there are two emitter, that means two diodes are going to be there and 4K resistance, they are giving you the normal AND gate which you have studied in 12th standard. This AND gate is followed by this inverter or a NOT gate, etc. And that's why the rest of the circuit only invert the signal, and that's why it is working as a 2-input TTL NAND gate. Now the question is this: in a NAND gate, what type of truth table is going to be there? If you look this truth table, the required truth table of the NAND gate is this. If A is 0, B is 0, output is going to be high. If A is 0, B is going to be 1, output is high. If A is 1, B is going to be 0, the output is high. If I want to combine these three conditions, then I can say that if any one of the input is low, then output is going to be high. When the output is going to be low, if both the input is going to be high, then and then only output is going to be low. This way I can explain the truth table, which can be explained by the circuitry also, how the circuit will perform these things. Think about this one. 5 volt is connected to the base through the 4K resistance. If A is low or B is low, low means it is connected with the battery ground terminal or negative terminal, that means 0 potential, and high means 1, that corresponds with plus 5 volt, positive terminal of the battery. So, if A is low and B is low, what happens? PN junction diode is going to be the forward bias, and hence the current will pass through that one, and voltage across the diode, because it is a silicon diode, will be 0.7 volt. The potential at base is going to be 0.7 volt only with respect to ground or with respect to A or B, depending upon whichever is going to be low. So, the potential at base is going to be only 0.7 volt. Now, between the base and collector also there is one PN junction diode. Now, for the transistor Q2, between base and emitter there is another PN junction diode is going to be there, and for the transistor Q4 also between base and emitter another PN junction diode is there. So, with respect to this ground of Q4, the potential of base of the Q4 should be 0.7 volt higher, then only this transistor will conduct. That means this potential should be minimum 0.7 volt to conduct transistor Q4. Now, to conduct Q2, how much potential is required? With respect to this, the potential of the base should be higher by 0.7 volt. That means 0.7 plus 0.7, at least 1.4 volt is required at the base of the Q2 to conduct transistor Q2 as well as Q4. Similarly, there is one more diode, that is base to collector diode, that is also required 0.7 volt, and that means with respect to ground, the potential of this base should be at least minimum 2.1 volt, so that this base emitter base collector junction of transistor Q1 is going to be forward bias, and there is a Q2 and Q4 will be conducting, and if it is less than that, this transistor will not be conducting. So, if either of this transistor is going to be at low state, that means A is low or B is low or both are going to be low, this is going to be forward bias, and potential here is only 0.7 volt, which is insufficient to see that transistor Q2 is conduct. So, Q2 is going to be off, and hence Q4 is also going to be off. So, these two transistors are not conducting. That means this transistor is off, means open switch, and the collector of this transistor Q4 is disconnected from the ground. Now, what happens about here? because this transistor is off. There is no collector current for this transistor. So, ICRL voltage drop across this resistance is going to be 0 because the collector current is going to be 0. So, whatever this potential is there 5 volt, that is going to be appear at collector of this one 5 volt will be there, which is going to be available to the transistor Q3 base. So, the base of this transistor is 5 volt will be there, which is definitely higher than the emitter potential, and hence the transistor Q3 will be conducting. So, you can see that Q4 is off, but Q3 is conducting at that time. Now, here we are taking the output from the emitter, and hence this circuit is acting like an emitter follower. What is the meaning of emitter follower? Emitter is following the base potential, that is called emitter follower. So, base potential is going to be approximately 5 volt. So, only the emitter potential is 0.7 volt down to that. That means output is going to be approximately 4 volt, and that means the output is going to be high. So, the first three conditions of our truth table is established. That means either A is high, A is low, or B is low. Then output should be high. So, this way the first three conditions can be satisfied. Now, we will see the last conditions. If A is high, B is high, then what happens? Then here the potential is going to be 5 volt, here also the potential is going to be 5 volt. So, base emitter junction of the transistor Q1 is going to be reverse bias. So, no current can flow in this directions. The potential maintain 5 volt, which is definitely higher than minimum requirement of 2.1 volt to conduct transistor Q2 and Q4. And hence, this base 2 collector diode is going to be conducting, or it is going to be forward bias, which will provide the current to the base of this transistor Q2, which is conducting now, and hence the transistor Q4 also will go into the saturation. When the transistor Q4 goes to the saturation, it is providing a closed switch between collector and emitter. That means output Y is going to be grounded. So, output Y is going to be low, and that is the condition of the last condition of the truth table. A is high, B is high, then output is going to be low. That is the requirement. You can see that if they are conducting, the voltage will be dropped across this resistance and the potential is going to be low. And when this is going to be conducting, still there is a possibility that this transistor Q3 may be conduct slightly. To prevent this thing, diode D1 is going to be inserted. So, it will provide the base 2 emitter diode plus this diode in series. So, that potential here is going to be insufficient to see that this transistor will not conduct at the time when Q4 is conducting. So, Q3 will be disconnected from the power supply and only Q4 is connected to the output, and hence the output is going to be low. This is the way 2 input NAND gate will fulfill or require 2 NAND gate truth table. Now, the same thing is going to be explained here. The output transistor Q4, Q3 and Q4, which is known as a totem pole connections. One NPN transistor is in series with another one. This kind of output stage is typical of most TTL devices. With a totem pole output stage, either the upper or lower transistor is conducting or on. When Q3 is on, the output is going to be high, and when Q4 is going to be on, the output is going to be low. The input voltages at input A and B are either low, ideally it is grounded 0 volt, or high, ideally plus 5 volt. If A or B is going to be low, the base of Q1 is pulled down to approximately 0.7 volt. This reduces the base voltage of Q2 to almost 0. Therefore, Q2 is cut off. With Q2 open, Q4 is also going to be cut off, and the Q3 base will pull high. The emitter of Q3 is only 0.7 volt below the base, and thus the Y output is pulled up to the high state. That is the first three conditions of our truth table. On the other hand side, when A and B are both are going to be high voltage, that is plus 5 volt, the emitter diodes of the Q1 stop conducting and collector diode goes into the forward conduction. This forces Q2 to turn on. In turn, Q4 goes on and Q3 turns off, producing low output. Table 14.1 summarize all input and output condition, that is truth table. Without diode D1 and the circuit, Q3 will conduct slightly when output is going to be low. To prevent this, the diode is inserted. Its voltage drop keeps the base emitter diode of Q3 reverse bias. In this way, only Q4 conducts when the output is going to be low. Totem pole arrangement. The totem pole transistors are used because they produce low output impedance. Either Q3 act as emitter follower, high output, or Q4 is on, which is nothing but output is going to be low. When Q3 is going to be conducting, the output impedance is approximately 70 ohms. When Q4 is on, the output impedance is only 12 ohms. Either way, the output impedance is low. This means the output voltage can change quickly from one state to the another state because any state output capacitance is rapidly charged or discharged through the low output impedance. This is the main advantage of totem pole arrangement. When the two transistors are working as a totem pole arrangement in series, both are NPN transistor, only at a time one of the transistor is conducting. If upper one is conducting, it is emitter follower, and output impedance is only 70 ohms. It is nothing but common collector configurations. Sorry. And when lower one is conducting, that output impedance is only 12 ohms, which is very low. You know that at output of the amplifier, there is a distribution capacitance that is called load capacitance or CL, which is going to be charged through this output impedance, and charging of this capacitance is take place through RG time constant. That means some factor maybe 0.69 or something multiplied by R into C. So if the value of this output impedance is very low, the charging time of the capacitor is very low. That means RC time constant is going to be very low, and it is discharging also very low, fast, because RC time constant is going to be low. What is the advantage of this one? The voltage across the output capacitance, which is going to be your gate output, which is going to be switching very fast from low to high or from high to low. That is, the output is going to be switching very fast, or propagation delay time is going to be very less. This is the main advantage of totem pole arrangement. Propagation delay time and power dissipation. Two quantities needed for later discussion are power dissipation and propagation delay time. What is power dissipation? Power dissipation is nothing but a gate require the amount of energy per second, joule per second, which is called watt, right? Per second, how much energy is going to be absorbed or it is going to be sourced by the power supply. That is called power dissipation per gate. That is nothing but voltage of the power supply multiplied by current drain from the power supply, and that is known as the power dissipation of the gate. So, two quantities needed for later discussion are power dissipation and propagation delay time. A standard TTL gate has a power dissipation about 10 milliwatt. It may vary from this value because of the signal levels, tolerance, etc. But on the average, it is 10 milliwatt per gate. So in our this standard TTL gate, this power dissipation is about 10 milliwatt. Milliwatt means 10 raised to minus 3 watt. Current will be in milliamperes. So if the current is supposed to be 2 milliamperes and you know that voltage is going to be 5 volt. So 5 into 2 approximately 10 milliwatt is going to be the power dissipation for our gate. But it can be slightly vary depending upon the signal levels, tolerance, etc. But on average it is going to be 10 milliwatt per gate. Second important quantity is known as the propagation delay time. Propagation delay time is the time it takes for the output of gate to change after the input have been changed. So, from one particular set of the input is given, output is some particular state. But when you change the input, output is not going to be realized immediately, but it takes some time, and then after only output is going to be established or set up. This minimum amount of time is known as the propagation delay time. The propagation delay time of a TTL gate is also approximately 10 nanoseconds. 10 nanoseconds means 10 into 10 raised to minus 9 seconds. Device number. Now, by varying this our standard TTL by Texas Instrument, they have produced the NOR gate, they have produced the AND gate, OR gate, NOT gate, etc. And the nomenclature is also going to be changed. So, by varying the design of figure 14.10, manufacturer can alter the number of inputs and logic functions. With only few exceptions, the multiple emitter inputs and totem pole outputs are used for different type of the TTLs. Table 14.2 lists some of the 7400 series TTL gates. For instance, the 7400 is a chip with 4 2-input NAND gates in one package. Similarly, if the IC is number 7402, it is also has 4 2-input NOR gates. 7404 has 6 inverter and so on. So, when I say 7400 series, it is nothing but TTL series invented by Texas Instrument. And if it is starting from 00, this last 2 digits which indicates what type of function inside that IC is going to be there. If it is 7402, that means it contains NOR gate. Moreover, there are 4 NOR gates are there in one IC, and each NOR gate is having 2 inputs. 7404 is a 6 inverter, and so hex inverter. You will see this numbering. 7400 quad 2 input NAND gate. Quad means 4 gates are there packed inside this IC. Each NAND gate is having 2 inputs. 7402 again it is quad, 4 NOR gates are there in a single package. Each is having 2 inputs. 7400 is hex inverter because 6 gates are going to be packed. These all ICs are normally of 14-pin IC. 14-pin IC means there are 2 pins will be utilized for the power supply, VCC and ground. VCC should be regulated 5 volt supply and positive terminal should be connected to the VCC and ground is supposed to be negative terminal of the power supply should be connected. Remaining 12 pins are available for different type of the gates. If your gates are having 2 inputs and 1 output, 3 pins are required for each gate. And if there are 12 pins, 4 gate can be accommodated. That's why it is going to be quad here. Here you can see that 7410, it is triple 3 input NAND gate. If the NAND gate which is having 3 input, 1 output, that means 4 pins are occupied per gate. And because there are 12 pins are available, only 3 gates can be accommodated, and that's why it is going to be triple. 3 NAND gates are going to be there, and each NAND gate is having 3 inputs. Similarly, 7411 is triple 3 input AND gate. 7420 is a dual 4 input NAND gate. 7421 is dual 4 input AND gate. if it is a 4 input, each gate require 5 pins because 4 input plus 1 output. So 5 pins will be required. You are having only total 12 pins. So only 2 gate can be accommodated. That's why it is called dual. So this way it is a nomenclature. 7427 is triple 3 input NOR gate. 7430 is 8 input NAND gate. It depends, number of input depends upon multi-emitter transistor Q1. Number of emitters maximum can be accommodated here is going to be 8 only. So maximum 8 input any gate is going to be possible. 7486 is a quad 2 input XOR gate, or actually it is OR gate will be there, XOR gate, exclusive OR gate will be there. So this is the important IC you will be utilizing. Now there is a commercial purpose series was developed as well as military purpose series was developed. You know, militaries are at a different places, maybe having a temperature is very low, maybe in the ice or somewhere, or maybe at the equator where the temperature is going to be very high, where their electronics equipments should work at a large range of the temperature and slightly unregulated power supply. And for that, another series was developed, and that series is known as a 5400 series, which is nothing but for military application. Any devices in the 7400 series work over a temperature range of 0 to 70 degrees Celsius and over a supply range of plus 4.75 volt to 5.25 volt. So actually it requires 5 volt, but variation of plus minus 0.25 volt will be tolerable. For 7400, that is commercial application ICs. This is adequate for commercial application. The 5400 series developed for the military applications has the same logic functions as the 7400 series, except that it works over a temperature range of minus 55 degrees Celsius to plus 125 degrees Celsius and over a supply voltage range of 4.5 volt plus 2 plus 5.5 volt. That means 5 volt plus or minus 0.5 volt tolerance is acceptable. Although 5400 series devices can replace 7400 series devices, they are rarely used commercially because of their much higher cost. Military applications is having the same logic functions, same number of inputs, everything, but their temperature range is going to be larger. They can tolerate little unregulated power supply, and hence these ICs are going to be costlier, which we don't use for commercial purpose. Now there are various type of the TTS. TTL is developed depending upon the requirements. Mainly the first we have studied is the standard TTL. Then sometimes it is required the speed of operation should be higher. That means the calculation computation should be made faster, and for that high speed TTL was developed. How to develop the high speed TTL? By reducing the propagation delay time. Propagation delay time TP depends upon RC time constant. So depending upon the value of R, that is called resistance, and the load capacitors or the output capacitors. Output capacitors we cannot change. So if you decrease the value of the load resistances inside the circuitry, that is 130 ohms can be decreased, 1.6 kilo ohms can be decreased, 1 kilo ohms can be decreased, 4 kilo ohms can be decreased. If these resistances are decreased, RC time constant can be decreased. But naturally, when the resistance are going to be decreases, so what about the currents? Currents are going to be increases. Current I is equal to voltage upon resistances. So if the resistance are decreases, it is inversely proportional to the current, and current is going to increase. That means power dissipation, which is nothing but voltage into current. So voltage is going to be fixed 5 volt. but current increases, so the power dissipation increases. So speed of operation is going to be increased with the high speed TTL at the cost of power dissipation. Remember, power dissipation is also going to be increased in high speed TTL. The circuit of figure 14.10 is called a standard TTL. By decreasing the resistances, a manufacturer can lower the internal RC time constants. This decreases the propagation delay time. The smaller resistance, however, increases the power dissipation. This design variation is known as a high-speed TTL. Now, how they are going to be designated? How you can recognize them? Sorry. Device of this type are numbered as 74H00. Here H stands for high-speed TTL. 7400 is a TTL series and H stands for high-speed TTL. 74H01, 74H02, etc. etc. This way it is nomenclature. A high-speed TTL gate has a power dissipation around 22 milliwatt. So from a standard TTL, it was 10 milliwatt, it is increased to 22 milliwatt. And propagation delay time of approximately 6 nanoseconds, which was 10 nanosecond in standard TTL. Now it is reduced to 6 nanosecond. That means speed of operation is going to be increased in high speed TTL. So this is second type of the TTL series. Now the third type. Third type is a low power TTL. Sometimes we require a battery operated system where the power consumption is more important. That means speed of operation you can compromise with low power. And for that, inside the circuitry, you can increase the value of the resistances. So if the value of the resistances are going to increases, that means currents in the circuits are going to be decreases. And hence V into I, the power dissipation is going to be decreases. So low power TTL was developed by increasing the internal resistances. So because the resistance increases, RC time constant increases, so the propagation and delay time is going to be increasing. That means speed of operation is going to be decreases. So that way the low power TTL was developed for battery powered system or digital system. Low power TTL, by increasing the internal resistances, a manufacturer can reduce the power dissipation of TTL gates. Devices of this type are called low power TTL and are numbered as, how they are numbered and how you can find out, 74L00 instead of H, which was high speed, here L is stand for low power. So 74L00, 74L01, 74L02, etc. These devices are slower than standard TTL because of larger internal RC time constant. A low power TTL gate has a power dissipation of 1 milliwatt. Compared to the standard TTL, which was 10 milliwatt, this is decreased to 1 milliwatt. And power dissipation or propagation delay time is going to be increased from 10 nanoseconds to 35 nanoseconds. So speed of operation is going to be lowered. So this way the low power TTL devices was produced. Now the fourth type is a Scotty TTL. Schottky or Scotty TTL. Schottky is the name of the scientist who invented this one. That's why it is called Scotty TTL. With a standard TTL, high speed TTL and low power TTL, the transistors are switched on with excessive current, causing a surplus of carriers to be stored in the base. So with this three main type of the TTL, that means standard TTL, high speed TTL and low power TTL, transistor go into the hard saturations because very high current, excessive currents are to be there when the transistor is conducting. That means extra charge carriers are situated inside the base, and when this transistor goes from on to off, then this extra carrier has to come out from the base. and this requires little more time, or this is called saturation delay time. And to avoid this saturation delay time, the Schottky diode was introduced. That means transistor does not allow to go into the hard saturation, but it remains into the soft saturation. So it immediately comes out from the saturation toward the cutoff Q points, and hence it save the propagation delay time, extra propagation delay time, saturation delay time, and hence the speed of operation is going to be increased. So this Schottky TTL is very important for speed of operation. With standard TTL, high speed TTL and low power TTL, transistors are switched on with excessive current, causing a surplus of the carrier to be stored in the base. When you switch a transistor from on to off, you have to wait for the extra carriers to flow out of the base. The delay is known as saturation delay time. One way to reduce the saturation delay time is with the Schottky TTL. The idea is to fabricate a Schottky diode along with each bipolar junction transistor of the TTL circuit, as shown in a figure 14.11. You can see that like this one. Between base and collector, there is one normal diode is there. Here there is a p-n junction diode. Normally, when this is going to be in saturation, the voltage drop across this diode will be 0.7 volt. That means it is heavily conducting. But this Schottky diode, you see the symbol of this Schottky diode. This is normally your anode, which is connected with this one base, and cathode, which is having this kind of wavy line also, which is known as a Schottky diode. The forward voltage drop of this Schottky diode is only from 0.25 volt to 0.4 volt only. This diode and the diode between base to collector, they are in parallel now. This voltage drop is lower, 0.4 volt maximum. This is going to be 0.7 volt. So it will not allow this transistor to into hard saturation, and hence it will not prevent the saturation delay time. Because the Schottky diode has forward voltage drop of only 0.25 to 0.4 volt, it prevents the transistor from saturating fully. This virtually eliminates saturation delay time, which means the better switching speed. This device are numbered as 74S stand for Schottky. So 74S00, 74S01, 74S02, etc., etc. So this is the fourth type of the TTL circuits. And you can see that along with the transistor, if there is a Schottky diode is there, the symbol of the transistor is like this one. The base is changed like this one. This indicates that it is with the Schottky diode. Schottky TTL devices are very fast, capable of operating reliably at 100 MHz frequency. The 74S00 has a power dissipation around 20 milliwatt. Here definitely power dissipation is going to be increased per gate from 10 milliwatt to 20 milliwatt. And propagation delay time is approximately 3 nanoseconds. So the propagation delay time is less than even high speed TTL. So if we say that this Schottky TTL has replaced the high speed TTL. In a high speed TTL, the power dissipation is also 20 milliwatt or something, 22 milliwatt, and the propagation delay time was 6 nanosecond. So it is lower than 6 nanosecond, that means speed of operation has increased. So virtually Schottky TTL has replaced high speed TTL in all applications. And the last one, which is known as a low power Schottky TTL. By increasing internal resistances as well as using a Schottky diode, manufacturers have come up with the compromise between low power and high speed, which is known as a low power Schottky TTL. Devices of this type are numbered as 74L00, LS00, 74LS01, 74LS02, etc. etc. A low power Schottky gate has a power dissipation of around 2 milliwatt and propagation delay time of approximately 10 nanoseconds. Remember these values. So here from Schottky TTL power dissipation from 20 milliwatt it reduced to 2 milliwatt only, and the power propagation delay time is slightly increased from 3 nanoseconds to 10 nanoseconds, which is of standard TTL. So it is acceptable, and that's why it is winner of all 5 type of the TTL. So out of the 5 type of the TTL, people normally utilize this low power Schottky TTL, which is known as a LS series. L stand for low power and S stand for Schottky TTL. So between 74 and 00 etc. LS is written that indicates low power Schottky TTL. Low power Schottky TTL is the best compromise between power dissipation and saturation delay time. In other words, of the 5 type of the TTLs listed in table 4.3, low power Schottky TTL has emerged as the favorite of digital designers. It is used for almost everything. When you must have more output currents, you can fall back to the standard TTL. Suppose you require higher load currents, you require higher fan out capability, then you can go to the standard TTL. On the other hand, in your applications, if you require a faster switching speed, then Schottky TTL 74S00 series is useful. Low power and high speed TTL are rarely used, if at all. Thank you very much, friends.